Welcome to this explainer. Okay, today we are tackling something that is literally reshaping the global economy as we speak. But, it often gets totally buried under dense academic buzzwords. We're going to demystify Industry 4.0. My goal here is to translate all these complex, high-level concepts into a highly practical roadmap for the modern smart factory. I really want to show you exactly how this shift is happening, not just in theory, but, on the actual factory floor right now. So here is a quick look at the roadmap for our journey today. First, demystifying Industry 4.0. Then, the 4 core foundations. Third, advanced machine intelligence. Fourth, theory meets practice. And finally, number 5, the human reality check. All right, let's jump right into Section 1, Demystifying Industry 4.0, Shaping the Future Today. Okay, let's dive into this. To really understand Industry 4.0, we're basically going to build the living organism of a smart factory, right from the ground up. Think about past industrial revolutions for a second. Steam power, electricity, early computing, those were largely understood only in retrospect, long after the fact. But Industry 4.0, it's entirely different. We are actively predicting, designing, and shaping this massive economic shift in real time. It promises completely new business models and massive leaps in operational effectiveness. We aren't just reacting to it, we are consciously building the whole shebang.
Moving on to Section 2, the 4 core foundations, the factory's nervous system.
So back in 2016, researchers Herman and his colleagues basically read everything. They distilled over 130 academic and industry papers to define the foundational design principles of this revolution. The very first principle they pinpointed, interconnection. This is the absolute basic nervous system of our smart factory organism. It means machines, sensors, and humans are entirely connected through the Internet of Things. It enables seamless collaboration across the board, human to human to machine, and machine to machine. But to make this work across different companies and suppliers, you need common communication standards so everything speaks the exact same language. And critically, because more connections mean a much larger attack surface, you absolutely must have robust cybersecurity.
Let's immediately anchor this with a concrete business example. Just imagine your supplier's inventory system is connected directly to your production line. The exact second your stock of a specific component drops below a certain threshold, the system automatically generates a replenishment order. No phone calls, no frantic emails, no delays whatsoever. That is interconnection in action, just a seamless, totally automated supply chain.
Principle number 2 is information transparency. Now, I need to clarify something. Raw data alone, it isn't enough. By continuously collecting data from physical sensors, the system actually creates what's called a digital twin. Think of it as a living, highly accurate virtual copy of the real-world environment. That data has to be analyzed and contextualized so it transforms into an actionable digital picture for the people and systems that actually rely on it. For instance, to put that into perspective, look at how this transparency directly benefits a logistics manager. Instead of just waiting around for periodic milestone updates, they can look at a dashboard displaying the exact location of every single shipment, the current condition of the product, like its temperature or if it's been exposed to vibration, and highly accurate real-time estimated arrival times. That is instant, actionable oversight right at their fingertips.
Now, the third principle, decentralized decisions, is arguably the most disruptive one of the bunch. Instead of a clunky central system routing every single command, intelligent cyber-physical systems take autonomous action right at the point of operation. They just handle the day-to-day decisions on the floor and only escalate true exceptions to human operators. It's a real game changer that drastically alters how factories operate daily. So, the crucial point is that this completely inverts the traditional management model. We are moving away from a top-down hierarchy where a central controller dictates every little move to a bottom-up, decentralized ecosystem where components actually self-organize based on the real-time info they have. And that brings us to the 4th foundation, technical assistance. As machines take over those routine decisions, the human role gets completely redefined. We go from being simple machine operators to becoming strategic overseers and problem solvers. Systems assist us virtually by aggregating data so we can decide faster, and they assist us physically using collaborative robots or cobots to handle the totally exhausting or dangerous tasks. To really bring this to life, picture a maintenance technician out on the factory floor. Instead of holding some thick, greasy paper manual, they're wearing augmented reality glasses. Those glasses superimpose step-by-step repair instructions directly onto the very machine they're fixing. It's entirely hands-free, it slashes error rates, and it perfectly illustrates how technical assistance is empowering the modern workforce.
All right, Section 3, Advanced Machine Intelligence, Upgrading the Brain.
So, if those first 4 principles built our nervous system, these next principles are all about upgrading the brain. Fast forward to 2021, and researchers Cassianis and colleagues expanded the framework, adding 3 advanced principles to complete our smart factory organism. Now, what's really interesting here is the clear distinction between making a decentralized decision and the newly added 5th principle, intelligence and self-awareness. While decentralized decisions are about what action is autonomously taken, self-awareness is about how the system understands its own role within the whole setup. A truly self-aware system knows its objective, it can auto-configure itself, and this is key, it can actually tolerate defects by automatically resetting when things go awry. To ground that, let's look at a pretty powerful example. Imagine you're on a highly automated production line, and a robot arm suddenly fails or loses calibration. Well, in a self-aware system, the line doesn't just halt and blare an alarm for a human to come running. No, it recognizes the fault, automatically rebalances the workload among the remaining healthy robots to keep production flowing, and independently orders maintenance for the broken arm. The production line literally heals itself. It's incredible.
Moving on, the 6th principle is knowledge, or continuous learning. Systems utilizing embedded machine learning don't just react in the moment. They analyze vast amounts of historical data to progressively improve their performance over time. Think of predictive analytics as basically the machine's ongoing education. For instance, a quality assurance system refining its defect detection model with every single batch it processes. It just keeps getting continuously smarter, without anyone needing to manually reprogram it.
And our 7th and final principle is interoperability. Now, this goes way beyond just basic technical connectivity. It's about frictionless data and service exchange across completely different manufacturers, totally bypassing silos and even varied business models. By using standardized architectures like RAM-I 4.0 and protocols like OPC-UA, you can basically think of these as universal digital translators. A company can seamlessly integrate data from, say, a FANUC robot, a KUKA robot, and an ABB robot all onto one single monitoring platform. No custom-built connections required for each one.
Okay, Section 4, Theory Meets Practice, Putting it to Work.
Let's look at an actual case study of a chemical company making the jump from theory to reality. This company completely revamped its internal logistics. The old way? Top-down centralized dispatching, where a central planner painstakingly assigned every single transport task. Well, they applied Industry 4.0 principles to create a bottom-up autonomous bidding system. Now, when a transport order is generated, automated guided vehicles, and even the human-driven ones, receive the data and literally bid in real time to win the order, based on exactly where they are and their availability. It's an ingenious, totally decentralized, self-organizing market right there on the factory floor. And finally, Section 5. The human reality check, lessons and challenges. Okay, it's time for a critical grounding phase, because while these concepts sound absolutely incredible, we need to consider this number, 95%. According to the research, a staggering 95% of Industry 4.0 concepts and studies are still just sitting in the laboratory. Only 5% represent actual, implemented, real-world industrial applications. So, the exciting theory is still currently running way ahead of our day-to-day practice.
And honestly, implementing that 5% comes with some major hurdles. Small and medium enterprises run a real risk of confusing digitization with unnecessary tech spending. Buying shiny new technology just for its own sake rather than actually solving problems. On top of that, cybersecurity is dangerously underfunded. As these networks expand, so do the targets for attackers. But perhaps most importantly, the human factor is so often overlooked. Workers require massive competency upgrades to successfully integrate with these advanced systems. Which leads us to a final, pretty provocative thought. As factories become increasingly self-organizing, interconnected, and autonomous, ask yourself, is your workforce actually being trained to strategize and oversee these complex ecosystems? Or are they still just being trained to operate machines? Because at the end of the day, a smart factory is only as brilliant as the humans empowered to run it.